Welcome back to ECE 320. We're still working with Laplace transforms, and one particular strategy or technique that will help us is to understand and be able to use operational transforms, and that's what we want to discuss in this video. Before we get into operational transforms, let's just remind ourselves of a few Laplace transform pairs and see that in fact those may not cover all of the particular types of signals or waveforms in the time domain that we might encounter, and for that reason it might be nice to have ways of not having to perform the Laplace transform directly on those new waveforms if in fact we can connect those new waveforms in the time domain to some particular property that will allow us to apply these operational transforms. And those properties might be, for example, a translation in time or a translation in frequency or maybe a scaling of the time axis. Those are typical modifications to these standard waveforms that we are used to seeing in Laplace transform tables that will be easier to take into the frequency domain if we understand how to utilize these operational transforms. The impulse is one of these standard waveforms. Again, you need to get comfortable with moving back and forth between the time domain and the frequency domain. Here it's simply crossing this vertical line from the left-hand side of the page to the right-hand side. But in fact, we need to be able to associate or connect frequency domain descriptions of these expressions or transfer functions that are ratios of polynomials in S to their time domain counterparts. The impulse is a constant 1. If it's a unit impulse in the time domain, that simply Laplace transforms into 1. The unit step transforms into 1 over s. We have a pole at the origin and no finite zeros. If we have an exponential, then we have a real pole in the complex plane on the real axis, and if it's a damped exponential, which it is here, we have an e to the minus 4t, that's decaying with time, then our pole will be located in the left half of the complex S-plane on the real axis. In contrast to that, if we have oscillating waveforms, here we have sine and cosine, which are pure sine and cosine. There's no damping involved with these waveforms, and we can write these sine and cosine waveforms in different ways. It's sometimes easier to think about it in terms of this first way that I've written sine, where I have sine of 5t for non-negative values of t and 0 for negative values of time, but you can rewrite that more compactly using the unit step function u of t to act like a switch, which u of t will only be non-zero for non-negative values of its argument t, and it's only equal to 1 since it's a unit step, so it's not scaling sine of 5t. It's really just turning it off and on at the instant when the unit step argument becomes non-negative. In this case, we have then what's the second expression in our x of t is exactly identical to the first expression for x of t, and we then associate those two similar or equivalent expressions to the corresponding transform in the right-hand column. And here we have the frequency, omega, in the numerator, no s, so we have no finite zeros in our transform of the sine waveform. And we have poles at the values where the denominator vanishes. And in this case, we have s squared plus 5 squared. If we set that equal to 0, we would see that we now have s equal to plus and minus j 5. Or we have poles right on the imaginary axis There's no damping if we're on the imaginary axis, and there's no growth if we're on the imaginary axis. We just sit there and shake. So now you can just imagine when you see this sine wave, you can just start shaking in your chair and imagining that just continues to shake without any kind of expansion or contraction due to there's no damping associated with that, and you would just keep shaking after somebody started you shaking at time t equals 0. It's transformed then as 5 over s squared plus the quantity 5 squared. You can compare that with the cosine waveform. Again, you can write it in both ways. They're equivalent ways of writing the cosine. The one-sided cosine, or the cosine that's starting or is defined or is non-zero for non-negative values of time, now its transform does have a finite zero. It has an s in the numerator, and the poles are in the same location. Since the cosine is shaking or oscillating at the same 5 radians per second that the sine was, that gives rise to those poles on the imaginary axis. We need to get comfortable with those, but we also need to become more comfortable with modifications of those classical looking or those more standard time domain waveforms. For example, what if we have a translation in time where now we're not starting at time 0, but in x sub 1 of t we're actually starting this cosine waveform at 1.5. What's going to happen to the transform in the frequency domain when we take this time domain expression or waveform into the frequency domain? Or what happens if we introduce exponential decay on a cosine waveform? In x sub 1 of t, how fast are you shaking? Well, you're shaking at a frequency, a radian frequency of 4 radians per second. In x sub 2 of t, you're not only shaking, now you're shaking at 5 radians per second, but in addition to that, at each point in time, you're being decayed by this product of e to the minus 4t with the cosine of 5t, and that then gives rise to this bounding decay of e to the minus 4t connected to the cosine of 5t, and that now makes this cosine waveform exponentially damped. You could also damp a ramp function in x sub 3 of t. X sub 3 of t, if it was just the t by itself, that would be a ramp, and you would know what that looks like in the time domain. That just keeps going from 0 up to infinity as time marches off to infinity. But in this case, what happens when we introduce exponential damping, where our damping now is e to the minus 5t, which is a little bit faster damping than we had on our cosine waveform here. And we want to get comfortable not only envisioning these waveforms in the time domain, but what they connect with or what they produce as from their Laplace transform in the frequency domain. And that's what we want to do. We want to develop some operational transforms, which are included in table 12.2 in your text, to help us move from these standard waveforms into something that we can see as a translation change, or a change in, or a translation in time, or a translation in frequency, or a scaling of the time axis. How can we now use that understanding to more quickly or more effectively come up with its Laplace transformed expression without having to explicitly compute via the integration process the Laplace transform of a more involved looking signal, which x1, x2, and x3 look a little bit more involved than what you're used to seeing. Even before we start talking about operational transforms, let's look at a related example, and that is this particular signal or waveform that's traditionally just called a pulse. Here we have a pulse of amplitude A. It starts at time t sub 1 and it finishes at time t sub 2. we would like to understand or see, can we find its Laplace transform? And we haven't had anything like this in the left-hand column in our transform tables necessarily, but can we produce the Laplace transform of this by simply utilizing some facts or connecting this z of t to more standard signals that are in the left-hand column of your transform tables? And in fact, we can rewrite z of t in terms of standard waveforms. Hopefully you can see that if t sub 2 never happened, or if t sub 2 happened way off into the right, maybe it's happening, maybe it never happens, then t sub 2 is infinite, then what happens? Well, now we just have a time delayed step of amplitude A. That would be like z sub 1 of t. But now, if we think of z sub 2 of t being a delayed step of amplitude A, just delayed by more time, and we take that away from z sub 1 of t, then beyond t sub 2, beyond t sub 2, z sub 2 is going to cancel z sub 1, and we will be left with this pulse waveform by combining z sub 1 of t with z sub 2 of t. And we know how to Laplace transform unit steps. We know how to Laplace transform delayed unit steps. Now all we have to do is invoke our understanding of the Laplace transform's linearity property, and we'll be done. We'll be able to compute the Laplace transform of the pulse, z of t, by combining the Laplace transform of z sub 1 of t and the Laplace transform of z sub 2 of t in the algebraic manner that is indicated in this relationship or connection of z of t with z sub 1 and z sub 2. And doing that, then, we can say the Laplace transform of the pulse is really just going to be the Laplace transform of z sub 1 of t minus the Laplace transform of z sub 2 of t. And the Laplace transform of a unit step is 1 over s. We've now scaled it by a, so now we have a over s. But since we're delaying this by a factor or by an amount, we're not starting our step until t sub 1, then that means that this transform actually gets scaled by e to the minus s t sub 1. T sub 1 is a constant. That's at the time t sub 1. That's now the Laplace transform of z sub 1. If that's the Laplace transform of z sub 1, we know what the Laplace transform of z sub 2 is. That's just the same, except now it is z sub 2 is starting later in time, and now we can actually say, oh, these both have an a over s. That would be an undelayed, or yes, an undelayed step of amplitude A, but now we are putting this in the form of a pulse. So let's go ahead and just say, let's put the A out front and the S down below, and now we have e to the minus s t1 minus e to the minus s t sub 2, and there is now our Laplace transform of a pulse of amplitude A. And we invoked, actually, a operational transform, which is this translation in time, that says if we do start a waveform, let's say we had the Laplace transform, and we're assuming, so in all of this discussion, we're assuming that f of t has as its Laplace transform capital F of s. We're assuming we know that. Now if we take f of t and not start it at time 0, but start it at time t sub 0, which is what this switch by utilizing the unit step is doing, all we're doing is saying, oh, let's just start our traditional function f of t at a time t sub 0 and move on from there, then that means that we would have in the frequency domain the Laplace transform of f of t weighted by e to the minus s t naught, where t naught is the amount of delay. That's how we treat or handle a waveform that's been shifted in time. That's the translation in time. If we translate in frequency, now we're translating in frequency, we're shifting s to s plus a. That in the time domain is equivalent to introducing exponential damping of an amount determined by what a is. Meaning if we now had f of t as maybe a unit step or even a ramp, but if it was a unit step, then we could actually find the Laplace transform of a damped step, which is really just the exponential, and that's now found by replacing s in our original transform with s plus a. That's the translation in frequency. And the scaling is now if we expand or contract by the choice of a we're assuming is positive, but it could be less than 1 or larger than 1. So we could be contracting or expanding the time axis. Then that not only changes the frequency, that's what this S over A does in the frequency domain, but it also introduces scaling of the amplitude of the transform by a factor 1 over A. So if we scale the time axis in the time domain, then we would then have to modify the original Laplace transform of f of t by dividing by a, and then everywhere we see an s in the transform, we would replace that with s over a. Let's now use this to see how we can actually utilize some of these operational transforms, and in particular this translation in time. Let's start with it. X sub a of t, that's the classic standard waveform. You could go into the table and find that, but at this point in the semester or in the course, you should be able to write that down. What is the Laplace transform of a cosine of omega t? And this is now a cosine, so the cosine now has a 0 at the origin. It's a pure cosine, so now we have a second order denominator, an s squared plus, and the constant in the denominator is determined by the frequency of oscillation, which is 4, and we square it. In this case, then, x sub a of s is s over s squared plus 4 squared, and we could have simply read that off from the transform table. That's a classical waveform. But now what happens when we translate that waveform or modify it by shifting it in time? Now we want to have a cosine of 4t minus 6 that's starting at t greater than or equal to 1.5. It kicks in at 1.5, and it just keeps going and going after time t equal to 1.5. What we want to do, and we could write that either as this curly bracketed expression or in a more compact form by saying let's just turn that cosine of 4t minus 6 waveform on with a switch, which we can create a switch using this unit step with an argument of t minus 1.5. That will not be 1 until t is 1.5 or larger, which is equivalent to what we have in the curly bracketed expression. Now what do? Well, we don't have cosine of 4t. We have cosine of 4t plus or minus some stuff. So let's see if we can work with the argument of the cosine and actually rewrite it or express it in a way that will allow us to identify or at least connect it with the amount of delay, which in this case is 1.5 units of time. Our cosine argument is 4t minus 6. Let's go ahead and factor out the frequency of that t so that we have t with some delay amount. So now we've factored 4 out of 6, and 6/4 is actually 1.5. And so you can see that I have created this to exhibit a consistent connection with the argument on the cosine and the amount of delay. Now you can see that cosine of 4 times the quantity t minus 1.5 u of t minus 1.5. Or we now have a consistency between the arguments of both waveforms. Cosine is now delayed by t minus 1.5, and the switch is starting at 1.5. This consistency is what we were after, and that now allows us to directly apply the translation in time operational transform. Now our function has the same argument, t minus 1.5, as our switch, which is u of t minus 1.5. That means that we take our original transform, f of s, which is the transform of a cosine. In this case, the cosine is s in the numerator, and it's s squared plus 4 squared in the denominator. And now we simply weight that by e to the minus s times the amount of time delay, which is 1.5. So we now have this scaled by e to the minus s 1.5, or usually it's a little cleaner to put the 1.5, the numerical coefficient, in front of the s. So here is our e to the minus t sub 0 s, and that's now the Laplace transform of that delayed cosine. And I hope that you're anticipating that a homework or an exam problem is probably not going to be that straightforward. So what happens if I give you now a problem where the argument of the cosine is not consistent in terms of the amount of delay in the time axis as the delay in the switch, or when we turn this cosine waveform on? Hopefully you can already see, though, that the frequency of this is not being changed by our factoring of the argument of the cosine. It's 3 radians per second. It's oscillating a little bit different frequency than the previous cosine, but that's not the point. What we can hopefully see is now if we really wanted 3 when factored out of 5 to give us 1.5, and that's not going to happen. But we can see that if we combine or break 5 into 2 parts, where one part is 4.5, that now has 1.5 buried in it 3 times. That's what we wanted, but we don't have 4.5. We actually had minus 5, and to get minus 5, we now separate it into 2 parts. Or this is now 3 times t minus 1.5. That accounts for the 3t minus 4.5, and now we have a minus 0.5. That's now in the argument of our cosine, so that x sub c of t is now the cosine of 3 times t minus 1.5 minus 0.5 u of t minus 1.5. Now what do we do? Well, this piece is the same as that piece, but we have an extra term in the argument of our cosine. But what we can do is we can now say, well, this is now the cosine of 2 angles. We have an angle A, which is actually a function of time, and we have an angle B that's now minus 0.5. We can now convert that so that when we do our cosine of A plus B, we can convert that into cosine A cosine B minus sine A sine B via a trig identity. And that will now allow us to only have a cosine waveform that might be scaled, but the cosine waveform part and the sine part will have a time domain argument that is delayed by the same amount as the switch. And what I want you to be comfortable with then is Appendix F and some of these trig identities. Here we're actually using the cosine of A plus B, where it's now cosine of A cosine of B minus sine A sine B. And you may not have those memorized, but you will be able to invoke those and have those on your crib sheet for the exam. So that now if we want to find the Laplace transform of that delayed cosine, we're looking at the Laplace transform of the cosine of 3 t minus 1.5 minus 0.5 u of t minus 1.5. Again, here is our A piece, and there is our B piece, and that now allows us to rewrite this expression on the right as a sum of two terms. We have the Laplace transform of the cosine of 3 t minus 1.5 times cosine of minus 0.5, that's the cosine A cosine B, scaled by u of t, or switched on by u of t minus 1.5, minus sine of 3 t minus 1.5 sine of minus 0.5 u of t minus 1.5. And now we have rewritten this so that we have consistency between our time domain argument in our cosine and the switch. We've now introduced a sine, so now we actually are combining sines and cosines to produce an original cosine waveform. And in this particular example, we have cosine of minus 0.5. That's just a number. That's just a numerical value which is going to scale this Laplace transform. It could be factored out of the Laplace transform. This sine of minus 0.5, this is just another number, and that now allows us to move a little bit further along in this Laplace transform operation so that we now have cosine of minus 0.5. That can factor out. Laplace transform of the cosine of 3 t minus 1.5 u of t minus 1.5 we now have changed the problem into where the cosine and the sine of minus 0.5 are simply weighting our result, which in this case, this cosine of minus 0.5 is just a scaling of 0.8776, and we can subtract from this cosine piece the sine piece, which is minus sine of minus 0.5, Laplace transform of sine of 3 t minus 1.5 u of t minus 1.5, and the sine piece taken in total is now going to be plus 0.4794, where this 0.5, if we wanted to sort of feel what that was, that, remember, if you're calculating that with your calculator, that 0.5 is in radians, and we need to now convert that, if you need to, in your calculator to degrees. That's now about 28.65 degrees, and that's now why the cosine of negative 28.65 degrees gives you 0.8776. That's not a really big angle. And the sine of a negative 28.65 degrees gives you a minus 0.4794, but we're negating that. And now we can combine all of these pieces such that we end up with the result that we wanted, which is 0.8776 times the Laplace transform of a cosine of frequency omega equal to 3. That's now s over s squared plus 3 squared. But remember, it's switched on a little bit later in time, and it's switched on, so we have to use our translation in time operational transform to produce this scaling of e to the minus 1.5s. And finally, we can connect that with our sine piece, which is 0.4794. The Laplace transform of this sine is 3 over, where 3 is our omega, s squared plus 3 squared. Again, it's delayed by the same amount, which then introduces this scaling of e to the minus 1.5s. That's the translation in time operational transform. Let's quickly look at one more operational transform, which is the complex frequency variable translation theorem, or really translation in frequency. So let me now just write that out in total. The complex frequency variable, that's S. The complex frequency variable is S, and we're translating that. So this is now the complex frequency variable translation theorem, or the S Translation Theorem, which says that if we have an e to the minus at in the time domain, an exponential damping of our original waveform f of t, that's pretty easy to find its Laplace transform. It's just if we have the Laplace transform of f of t giving us capital F of s, then everywhere we have an s in that expression, we replace it with s plus a. As an example of that, suppose, well, we know what the Laplace transform of cosine omega t is, or if we don't know, we better start becoming very comfortable with that. That's s over s squared plus omega squared. And now if we had an e to the minus 4t cosine of 3t u of t, so there's no translation in time. Now let's look at this in parts. If we didn't have this piece, what would we have? Well, we would just have the classic Laplace transform of a cosine. So that would give us s over s squared plus omega squared. But now that we have this exponential damping on top of our, or damping out our traditional cosine of 3t waveform, that says that we now replace, everywhere we have an s, we replace it with s plus 4, where 4 is the a in the exponential damping, and here we then have s plus 4 being replaced, so that in total, when we put all of these pieces together, the Laplace transform of an exponentially damped cosine waveform is now going to be s plus 4 in the numerator. We now have a 0 at minus 4, and we have s plus 4 quantity squared plus 3 squared. And you can think about what we have in terms of, if we looked at the standard waveform, which is cosine omega t u of t, assume that that's a constant omega, then that produces in the frequency domain a pole zero pattern. There's no exponential damping, so that now we have a zero at the origin, and we have poles at j omega and minus j omega. Compare that with a waveform that has damping in the time domain. Suppose that we now looked at what we just Laplace transformed, e to the minus 4t cosine of 3t starting at time t equals 0. Here is time. Now we have this exponential decay, and we have a cosine inside that envelope. So that instead of having a cosine of 3t, which might look something like that, now we have, and I probably shouldn't have put that in there, now it's going to make my job a little bit more challenging, but we now have an exponentially damped cosine waveform. It's damped by that decay amount, and what does that do in the S-plane? That's what we have over here, except now we are shifted. Remember that we had a frequency of J3 and minus J3, but what do we have up here? We have a 0 at minus 4, and we have a pole actually at minus 4 plus and minus J3, and this pole 0 pattern now indicates that the damping has pushed these poles further into the left half plane. This is now the damping associated with the e to the minus 4t term. And that now has changed or modified our pole 0 pattern in the S-plane associated with the Laplace transform of that exponentially damped cosine versus just a pure cosine that has, in terms of its pole 0 pattern in the S-plane, a pole at the origin and, a 0 at the origin and poles on the imaginary axis at plus and minus j omega. Again, that's an illustration of the complex frequency variable translation theorem, complex frequency variable S, and we're translating that in amount A consistent with the exponential damping in the time domain introduced by this e to the minus at factor that scales our original waveform f of t.